Okay, welcome everyone to this webinar. We've titled it, Are Lean and Computer Simulation Compatible? ? And that's the idea we're going to explore in this, what may be a series of webinars. And let me just share with you who we are, introduce ourselves first, and then we'll get into what triggered this line of thought. I'm Richard Rahn. I'm a principal with the Leonardo Group. Gerard?
Hi, I'm Gerard. I'm a principal with the Leonardo Group too. And one of the key reasons for this webinar is because we've been hearing from some of our students and also from other sources this concern about the compatibility between simulation modeling and lean thinking. With lean thinking apparently advocating, well, instead of simulating something, why don't you just go out to the shop floor and test it live? Well, we're going to make a case for you today that simulation modeling is a much safer way of designing a line. Now, if we're talking about a line that is 2 stations with just screwdrivers and bits and pieces, well, yeah, sure, no risk. But if you are like one of our clients building highly complex, heavy products, well, the risk is much, much higher, and you should seriously consider modeling your line before bringing it live. So that's going to be our point. And we're going to get going first. The first part of the discussion we would like to have with you is what skills are necessary to build a simulation model that is going to give you good information for your line design. So Richard, let's get started with our list of the 5 required skills for building a good simulation model.
Great. So we're talking about what are the first steps, the first prerequisites you need to have before you can even really get started. And first and foremost, especially from our point of view, is what we're calling the roadmap, the line design roadmap, or the methodology is another way of saying it, that you want to follow. So we're clearly saying here that you don't want to just go out and try to model something without having a structure or framework that you're working with or using. And the line design roadmap is what we've been teaching for many years. We have online training, and it basically walks you through the methodology that includes simulation, but it includes a lot more to get you to the perfect value stream or the ultimate value stream. So without that foundation, you're really opening the doors to a lot of random efforts that may lead you astray. So if you're not familiar with the roadmap, there are many opportunities to learn more about it. But we're taking that as a foundation assumption that we're working with the line design roadmap. And simulation takes place as a part of that journey, but that roadmap includes a lot of other phases, a lot of other aspects in terms of developing the ultimate value stream.
Exactly. You would never hear from us or from anybody who knows anything about designing a line. Here, Richard, here is a simulation package. Go and design me a line. Never. That's a recipe for disaster. From our standpoint, and again, from anyone who knows anything about designing a line, you get to the point of building a simulation model because you have already gone through all the data gathering, the data validation, understanding the standard work, calculating the number of resources, figuring out in-process Kanbans, and coming up with a conceptual line design. At that point, you start talking about building a simulation model. Before that, you are shooting in the dark, and it's going to be a very risky endeavor. So, number 1, you need.
I think related to that comment is this idea of Kaizen. The idea that you can just go out and improve something without really a methodology by applying lean thinking or being the smartest guy in the room. When the topic of simulation comes up in the lean community, what you often hear is, well, that's not necessary. We can Kaizen it, or we can go out to the Gemba. We can improve a process just by engaging the team and working with, with the folks on the factory floor, for example.
Throw the line together, throw the light together, and then Kaizen it, right?
Yeah.
So
Yeah.
I assume that someone could say, no, don't worry about testing that aircraft in a wind tunnel. Throw it together and then see what happens.
Yeah, let's build the airplane and then we'll fly it and then we'll see if it works. So no one does that. Why don't they do that? Well, because they don't do that because the potential risk is so high, right? That someone can die. Now, if your factory line or your value stream doesn't run as expected, maybe no one dies, but you're still going to waste a lot of time and a lot of money fixing it later. So we're trying to avoid that, obviously. Okay.
So number one. Number two.
Number one was the roadmap, right?
Yeah.
Okay. Number two on our list. And this is definitely part of the roadmap. It's data collection, the step of data collection. You're building a model. That model is a mathematical model. And no matter what software you're using, you're going to have to enter data into it. Processes, times, demand, products, all those kind of things need to go into your simulation model. And of course, into any kind of line design, you're going to go out and gather data. So the data collection phase on the roadmap happens before simulation, right? Before you can build the model, obviously. Now, is there any data that you may not have gathered when you get to the simulation stage that you may have to go back and get? Possibly. It depends how much time you spent really looking at this issue of variability. So if you've only gathered average times, or you have a very small sample, or you haven't drilled down deep enough in terms of the characteristics of that data, you may need to go back and do some more work, because that's really going to be important to be able to build a model that reflects reality. Clearly, if you build a simulation model that does not reflect reality, then no one's going to believe it, no one's going to be very impressed, and you're not going to be getting any useful output out of that. But basically, data collection happens before you get to the simulation stage, if you've done it right.
And this data collection skill also includes your interviewing skills, being able to go out to the floor and ask the folks that do the work, well, yeah, I see that in the routings, this is, for this product, we have 3 minutes worth of work content. Bob, you do this work every day. What can you tell me about this? And you will start understanding the variability then, because people will tell you, oh yeah, but when this one product comes over, it is very unpredictable, or this one has not yet a very solid design or a mature design, so it takes me a lot longer to do the work. Now you begin to understand the extent of variability, and variability is the reason why you do a simulation, why you need to do a simulation model, because variability is going to come from multiple different sources, not just from the fact that you have humans doing work, and humans cannot always hold the time like a robot, and that's important, but also there is a variability in the work content due to factors like the products come in different sizes. Sometimes the parts don't fit the same way depending on the product. So multiple different sources of variability. Make sure that you go to the floor, you ask. Data gathering is not just an exercise on looking for data out of your computer systems or engineering records. You need to go out to the floor. So interviewing is a very important part of your data gathering skill.
There may even be unspoken rules or undocumented processes out on the factory floor. I remember, Gerard, you told me a story one time of a line that you were working with, and on second shift, this woman came in, a machine operator, and she had a little bag, and she had her own special tooling, and no one had been able to figure out why the throughput on her shift was so much better than on the other shift. Well, she had this little tooling that her husband who was a machinist, had developed for her.
Yeah.
Totally undocumented, right? Unapproved, but she did it for her own benefit, right? And it worked. but not on the books, not documented. So how would you ever know that unless you really got down to the floor and interviewed these
Unless
people?
you're out there. And the number of times that I have been told on the floor while checking on data that we put together with the line design team, the number of times I've been told on the floor, oh yeah, that's the way it's documented. Oh yeah, that's the way it's in the routing. But if we were to do it that way, we would never finish. Enormous. So go to the floor, interview, talk to the people. So make sure you learn that skill and you hone that skill.
So let's recap. We've got use the roadmap, number one. Number two, there's a data collection phase as a part of the roadmap. And maybe to supplement that, you need to have good interview skills and go out on the floor and really dig deep in terms of how things are actually working, right? So that's where we are so far in our skill set. Mm-hmm. So what's next? Computer skills, what we're calling computer skills.
Yes.
Now, in the past, and it's still true today, if you wanted to build a simulation model, every software company in the world is going to show you how or tell you how easy it is to develop a simulation model. But what you're going to find, I'm afraid, is that with most packages, as soon as you get beyond a level of pretty simple, you're going to have to do some coding or really involve yourself in a deeper level in terms of how that software works. And it's not always as simple as just putting in some numbers and pushing a button. So in some cases, the skills that may be required, depending on your software, actually are somewhat programmer related, programming type skills, deeper skills than most of us usually have. But even beyond that, we're still talking about computers, using computers. So the skills of just gathering data and being comfortable with data manipulation and using Excel spreadsheets, all of that, you need to have. If you don't have that, if you're a complete novice, and not too many of us are these days, but if you're not, then you need to beef up that part of your skill set as well. And in terms of the difficulty, the computer knowledge required, we've done something to address that with the Lean Design Simulator, where really your level of knowledge is more on the level of using Excel well, as opposed to having to do any kind of coding or programming, because we've essentially taken the simulation piece of it and put it into a black box and insulated the user, from that kind of complexity.
But so Richard is right on that. If you have an aversion towards computers, well, that's pretty much a showstopper. You will need to use a computer, and then the level of skills will depend on the package you have. What we are trying to do to address what was a big source of frustration for us the first time we talked about simulation with Richard was back in 97 or so. And we looked at a specific package,
before many of you were born, right?
At a very, very high level package that we loved, and we could have learned it, but the commitment to learn it would have meant having to become experts on that. And we are experts on line design. Simulation, we see it as one more tool. And then there's just one package, right? So what we want to do with the Lean Design Simulator is to simplify it. So with Excel skills, you can build a simulation model and test for the big or the most important aspect of a line design. No, I don't know if the most important aspect, a very important aspect of line design, which is the variability in the work content.
Okay, so computer skills. And then the last thing we wanted to address is really related to what you do with your results, what you do with your model after you've run experiments and come up with some improvement ideas or suggestions or a more robust design. Typically, you may not be the one in charge of actually implementing that. You have to convince other people that the analysis that you've done, the simulation results you've achieved are correct, and you need to go down this new direction and improve the design in this specific way. In other words, you're going to have to sell your idea to other people. Maybe your boss, maybe your boss's boss, going up the chain. So in terms of a complete package, in terms of a complete ability to deliver value, as a simulationist, you need to be able to convince other people that what you've learned and the changes that you've made are worthwhile pursuing. So presentation skills or salesmanship, if you want to call it that way, are going to be a part of it too. Because it's a little disappointing. You can appreciate if you go through all this effort and then you can't convince people that this is the right direction to go. And that happens. I guarantee you that actually does happen, where you go through all this work and then you can't convince the management team or anyone that has that responsibility to take that next step and do it.
Well, Richard, one of your line designs, you and the team going through
I deny
the roadmap. Yeah, going through the roadmap, you calculated, I believe, that you needed 7 workstations, right? Substantial workstations, because all of them require a substantial number of resources. And after a 3-day encounter with your team, going over multiple different scenarios and simulation, as a team, you decided you needed 8 workstations. Yes, the static line design said 7, but you were able to justify 8. Now, if that 8th workstation costs $2.50, no big deal. But if that extra workstation takes a substantial amount of space or many more resources that cost money, now you have to be able to convince the folks that are going to write the check that this is worthwhile. It's not just the results of the static calculation. Now the dynamic simulation tells us that to achieve the throughput that we want so the line can deliver to customer demand, here is the end result, and this is going to cost us a little more. And
I know what example you're referring to. That adding that one station was tens of thousands of dollars. That was not a cheap one. Fortunately, we didn't have to struggle too much with getting that approved because we had management folks on the team, right? On the team that had gone through that analysis and understood the necessity to add that additional station. I know another story though along these lines of selling things. I think this happened long enough ago that I can share some of the details. But it was Compact Computers was building a new warehouse. And they had this challenge of having to stage orders prior to shipment, and they wanted to have some idea of how much space they needed, right, to hold the orders before they could fill a truck, say with a complete order. They couldn't ship individual computers. Sometimes they'd have to wait and ship the order complete. Could be 100 PCs going together. So they hired a simulation company that I happened to work for, full disclosure, some time ago, and they had estimated in Excel, kind of on the back of the napkin, that they needed about 25,000 square feet for the staging area. And when they built a model and modeled this, the simulation result was 100,000 square feet, and the sales effort to convince them that that was a correct analysis failed, and as a result, then Compact went with their estimate. They liked 25,000 square feet a lot better. And further down the road, when they actually started to run this factory and use that space, they quickly filled it up and ran out of space. And it was a huge issue later on. And the simulation company received an apology letter from the president sometime afterwards saying, "We gave you guys a hard time and you were right. You were right about that space needed." So anyway, we're just saying here that at the end of the day, you need to be able to sell your ideas and your results, and it should be fairly easy to do because you've got data, right? You actually have a model. It's not your gut feel. It's not your intuition. It's actual hard scientifically based data, but you still have to sell it, right, to someone to take action.
All right. So I think we're going to be moving on to the next set of topics. And the next set of topics will be the prerequisites to building a successful simulation model. And welcome everybody to our second webinar on this series of webinars on the application of simulation modeling to lean mixed model line design. On the first webinar, we talked about the required skills to build a simulation model. Today, we're going to discuss the prerequisites or success factors necessary to build a good, solid simulation model that is going to give you the data you need to make the right decisions. So with that, let's get started with the first of these success factors. And I think that the best way to put it is, or a short way to put it is, have clear goals. So this may sound almost obvious, you need to have clear goals, but let's dig a little deeper into that. Why are you building the model? Are you building the model to prove the throughput of the model? You design a line that with the goal of building 387 units a day. You build a model. Is the model giving you the 387 units a day? So that is one goal, one very important goal, and you need to make sure that you are pursuing that goal throughout the testing of the simulation model. So what else could we be using a model for?
Yeah, so throughputs would be a very common goal to test the throughput of your line, of your design. But there are many others. For example, you might be highly interested in labor or efficiency improvements, productivity gains. And let me highlight why defining this up front would be so important. If your goal, one of your primary goals, is to really look at productivity gains, and you don't define your labor resources in the model at sufficient level of detail, you won't have the information you need to really drill down and identify those opportunities for improvement. For example, you can have a model with one labor category, one single labor category with multiple people, but that may not help you zero in on where that utilization is lower and where the opportunity for improvement lies. So you would need to, if your goal is productivity gains, you need to define those labor resources at enough detail to allow you to achieve that. Another example, let's say that the goal of the model is to develop sequencing rules. If you haven't defined your products in that model in enough detail, you won't be able to create sequencing scenarios to test to determine what your optimum sequencing rules are. So maybe you just have what we call representative part numbers in the model. That's not going to help you develop those detailed sequencing rules. So defining very clearly up front what it is you want to get out of this model will help you determine what kind of data or at what level of detail you need to be thinking to achieve that goal or to achieve that result. Make sense?
Absolutely. And I remember in one of my projects, Richard supported me at a distance with simulation modeling, and for one section of the line, we tested 8 different ways of sequencing product, 8 different scenarios, and on each one we tested different ways of sending the product down the line, and chose the most streamlined one for the final line design. So again, designing a line is not just figuring out the number of resources, the linking and balancing, but also how you make the line work. And simulation model is an invaluable tool in figuring out how to make the line work. All right?
Okay, I think we got that one.
Yep.
All right, next success factor. It's going to be really problematic, I can guarantee you, if you're not sure that the model is working correctly. That's almost too obvious to need to say. But if you don't trust that underlying design or underlying function of that model, then everything else is for naught, right? It doesn't matter what numbers, what data you put into it, you're really not going to trust that output. So before you take that step, highly recommend that step of actually loading data. You want to make sure that the basic infrastructure of that model is working correctly. For example, if you have a spur in the flow, 20% of the volume goes in one direction and 80% goes into another. Maybe it comes back together later on. You want to make sure that that's actually what's happening in that model, that 20% are being diverted in one direction, 80% in another. Now, how do you test it? Well, one technique that I use, that we use, is you build the model with all of the connections, all of the routings or all of the flow definitions, the products, etc. But in your time, your process time table, instead of the actual process times, you just put in a value like 1 minute for everything. And in that way, you can actually look at the output. And if you have 1 minute work content time, you should be able to get 1 unit per minute as a throughput. And you can actually look at the detailed throughput in each of those processes in the model in a way that you can actually understand. So what I always do when I build the models, I don't assume, even though it runs, right, it's not crashing, I don't assume it's running correctly until I go through that kind of check and make sure that everything is connected properly, that any kind of percentages that we've entered into there are actually working as intended, so that when we go to the next step and start adding real data into it, I don't have to worry about this idea that, hey, is it running? Is it working right or not? I already have that confidence.
We always do it in steps. We build it gradually. First, you build the model, then you run it with no variability and 1 minute times. So if you run the model for 420 minutes, how many units should you get? Exactly 420. No variability, 1 minute, right? Then you take it to the next step and start adding real data. You run it without variability, then you add the variability. And the next step brings us...
Well, before we leave that one, and if you don't, the point is, if you don't get the expected throughput number, or the throughput in any individual process, that is a bug, right? And you've got to fix it, right? So great opportunity to zero in on where that problem is, and you fix it in the model. And then you can go on to our third success factor. Gerard?
Yep, and that is testing the model with current state data. So it is unlikely that you will be designing a line that doesn't exist. It happens, but normally what happens is that there is an existing line, we redesign it to make it better, right? So the line exists already. So you can tell that this line with the current, in the current conditions, yields 123 units per day. What we're going to recommend is that you take the current state data, load it into the model, and run it. And if the answer from the model is that with those conditions, you should be able to get 385 units a day, now we have a problem, right? Because you're good, you're not that good. So design or run the model with the current state data, and that should give you a good degree of confidence, or the result should give a good degree of confidence that your model and your assumptions are correct.
And typically you'll find problems in a couple areas. Once you have confidence that the model actually works, that things are connected properly, things are flowing the way you expect, and then you enter data, actual data, you're going to find potential problems in a couple areas. Number one is going to be your process times. So if your process times are not correct, the times you entered, you're going to have a variation in the throughput compared to how many you're actually getting and how many the model is producing. So that's one big area where you could anticipate probably having to go back and take a second look, process times. The other thing is process variability. So if there's variability happening that you didn't capture, the same thing's going to happen. Your actual throughput may be lower than what the model is showing. You're getting more units through the model than you're actually getting in reality. Again, one root cause of that could be you're not capturing some of the variability that's actually happening on the factory floor in the model. And both of those things really need to be addressed, right? But having the current state and then testing against the model is a great way to highlight or raise a flag on those issues.
So To bring this to a close, on the first webinar, we talked about what are the skills necessary to build a simulation model. Today, we talked about what are the success factors or prerequisites, right? With those being have clear goals, build the model and prove it, and then run the model with current state data. With that, we're going to bring this webinar to a close, and we will see you on our next webinar, which will center around the benefits of using simulation model for line design.
Okay, see you next time.
See you next time. Thank you.
Okay, we're back. We're live. Welcome back, everyone, to this webinar. And we're continuing on our journey here. So far, we've talked about a couple different aspects to building simulation models. And what we're trying to do is answer this question, are lean and simulation modeling compatible, those two things? And we're trying to make the case, I think, for the answer is yes, but we want to really dive deep and really prove it to you. So in the first couple sections, we talked about the skills, kind of necessary skills to be successful with computer modeling. And then in the second webinar, it was some of the success factors or the prerequisites to make sure you have a successful result or successful outcome from an effort of building a simulation model. So now let's continue on that same vein and talk about the benefits. So specifically, why would we want to take the time and effort to develop one of these simulation models? There are many reasons, but we'll be addressing the 7 most important ones in this webinar. Okay.
And in general terms, when we are teaching our mixed-model line design workshop live at a client site or the class we teach at Toyota, one of the points we make is that when you go through the mixed-model line design roadmap, you will go through a series of steps of data gathering, data validation, calculation of resources. You will get to a point at which you have a conceptual design, and you will have to go through a step of balancing the work content. You will balance that work content statically because that's all you have. You have a static model, right? A static mathematical model. You will have to balance the line, distribute the work content across all the different workstations. That is one milestone for sure. There is another milestone, and that is when you bring the line live, you will have to balance the line. Regardless of how good you were at balancing the line on paper, you will have to balance it when you bring it live. Now, to minimize the amount of rebalancing that you have to do and to increase the probability that when you bring the line live, it will yield the throughput that you expect, we're proposing a step in the middle, and that is to balance the line and to prove the line design by using a simulation model. So the benefits that we're about to discuss are related to what should you expect or what will you get out of building a simulation model. So should we go through a list?
Yeah, let's do it.
Okay.
Let's do it. So the first one, first of the 7 is test without building it. Test without building it. So that's a big one. And that ties back to some of the initial pushback that we heard or that we saw online from our Lean community. Hey, don't build a simulation model, just go do it, right? Test it in the real world. But you don't want to do that, my friend, if that testing is going to be very expensive to change, or there's a lot of uncertainty involved with the design. And the example, I think we've talked about this a couple of times already, you don't build the airplane and go fly it to test it. You test it in a simulation environment, which we call a wind tunnel. Or I'm sure they have electronic wind tunnels these days. But you test it in a model kind of environment to debug it, get it very close, and then you take that step of having to create it in the physical world. So testing it without building it is a really, really important thing. Unless you have a design that's really simple, right? Cheap, small, easy to change. Okay, you could make a case that you don't need to test it ahead of time because it's very easy to fix.
Is your line the equivalent of an ultralight, or is your line the equivalent of an Airbus A380, right? Of course, those two are different. The A380, you better put it in the wind tunnel. The ultralight, well, the wind tunnel is going to break it. So,
yeah. So very, very important, because the very, very most expensive, worst time to be fixing something is when you've already built it, obviously. So there was an article a couple of years ago by Jim Womack who really made this point very clear. He asked the question, why are we seeing so much Kaizen in many companies that he visits? They're very proud of their Kaizen programs, but why is so much Kaizen needed? And he made the point that at mature lean companies like Toyota, this post-implementation Kaizen is a relatively minor part of their total strategy. It's not a major focus. And why should it be if you do it right the first time? Okay, so simulation modeling is a way of achieving that.
Please do not interpret this as we are the guys who are against Kaizen. Absolutely not. Kaizen is a necessary aspect of any lean initiative. But you also need to know that no amount of Kaizen will fix a bad line design. You start with a solid line design, then you apply Kaizen. That's the way you should do. All right. So First of all, test it.
Got that one?
Or you build it.
Right. Number 2, test many iterations.
Yes, you can run a full day of production in 20 seconds. So how many days of productions can you test in an hour of exercising different production sequences? You can get a lot more information from a few hours worth of simulation than from days and days and days of observing on the line. Again, do not interpret this as us saying don't go to the shop floor. Of course you have to go, of course you have to observe, but you get to see a lot more and a lot quicker with a simulation model.
Now, it goes without saying, but I'm going to say it anyway, that at this point you have confidence in the model, right? You have confidence that the model is modeling reality. And therefore, these iterations that you're running through are a close approximation of what actually would happen in the physical world. That's an underlying assumption, but it's a good one. If that's not the case, then you need to take a couple steps backwards and make sure that that model is reflecting reality correctly. But once you have that, you can run, as Gerard said, you can run through in simulation time, which is a fraction of actual elapsed time, many, many different combinations, experiments, compared to trying to actually physically do it in the real physical world. So big advantage there. Do a lot of testing. And this is especially important, by the way, in a mixed model environment where the number of combinations of products, of mix and volume is almost infinite. So to think that you're going to be able to test a mixed model line in its many possible combinations and variations in a physical world is just never going to happen. Whereas in a simulation environment, you can really test many, many, many combinations.
In one of Richard's projects, where every workstation would have costed a very substantial amount of money and space, Richard spends 3 days with the entire line design team and the management team running through different simulation scenarios, right? And by the end of the 3rd day, and then again, that's a minor investment considering the expense of a major line, right? At the end of those 3 days, they had very solid, reliable data to start building the line. And they started building the line after that. So that is what we're talking about. Maybe a day, maybe 2, in the case of this line, maybe 3. But with that, you will have much more reliable data and a much higher degree of confidence that your line will do what you designed it to do.
You know, and here's an interesting point. We're saying simulate before you implement, but actually it's a little bit even before that. Simulate before you create a final layout, even.
Yeah.
On the roadmap, you have what we call conceptual layout. That's more of a block flow. And right after that is where the simulation piece would come in. Because why would you want to create a CAD layout that you're going to be making a lot of changes to later on based on your simulation results? So the benefits of doing the simulation save you not only implementation time, but actual CAD time doing the final detailed layout. Yep. Okay. Next benefit, we're calling this forces deep understanding. Forces deep understanding.
Yeah. To build the model, first of all, you're building the model because you already gathered all the data, did all the resource calculations, balanced the line on paper, created the conceptual design. So you already know what you're doing. Now you're going to dig a little deeper. You're going to delve deeper into the details of each process, looking primarily for that variability of work content. So by the time you run all the simulations, you have a very deep understanding, not only of the line globally, but also of each individual process. So you will know your processes, your product, your work content, and your line a lot better by going through the process of building the simulation model and running the simulation.
So that deep understanding really comes from trying to make sure that that model reflects reality. And when it doesn't reflect reality, you need to dig deep and find out why not. And in the process of discovering why not, you learn new things that maybe you didn't know before. That could be undocumented processes. It could be, workarounds. There could be a lot of things happening that you may or may not be aware of. But in the effort of matching your model to reality, you're required. You will be forced to really dig deep and understand things at a level that you maybe never had to do before. All right, happy with that?
Yep. Let's move on to the next one.
That's a good one. Next one is generates valuable metrics. This is a good one. Want me to tackle this one, George?
Yes.
Okay, so metrics. So measurements of performance, throughput, utilization, time spent working versus time spent waiting versus time spent blocked versus idle, no demand. All those details are part of the output you will get by running the simulation model. Now, if you didn't have the model and you had a live line running, and you go out there and observe it, you might try to make the case that that's better. But in point of fact, observing the line running will not allow you to actually see or drill down to that level of detail to gather those kind of metrics. You can imagine if you have a line with 20 stations, are you really going to be able to know what percentage of the time the buffers or in-process Kanbans are full or are filled in between each individual station? There's no way you're going to gather that data. Or the actual value-adding utilization of each operator on the line versus waiting time or versus block time. There's no way you're going to know that by simply observing the line. And yet that is part of the output that you'll get from a simulation model. Now, keep in mind, remember that we're assuming that this model is reflecting reality. But if that's the case, then you're getting all kinds of information that there's no way you would get by simply looking at a line that's running.
As a matter of fact, depending on the simulation modeling package you use, you may get too much data, right? One thing that we tried to do with our lean design simulator was to streamline, better said, minimize the amount of data we provide you that goes to the heart of what matters on every process when you're running a line, right? But if you have a line with 20 workstations, and believe me, we have had lines with many more than 20 workstations, and then all the IPKs and all the different types of labor categories you may have in that line, there is no amount of observation that will tell you station by station, IPK by IPK, what everybody is doing. You will get that from a simulation model, and that will make your chances of success much higher. Again, we are not advocating for replacing observation. We're adding this to increase your chances of success.
And part of your goal in becoming a good simulationist would be your ability to look at that output data, right? To analyze that output data and really understand what it tells you and be able to identify where are the bottlenecks, where are the opportunities for improvement. That's part of, should you get into simulation modeling, that's part of your job to get good at, to be able to look at that output and really interpret it, right? And make good use of it. All right. Next benefit, learn new things. Learn new things.
There is, in this one, I think that this one can be said in very few words. There is no way that you will build a model, run the model, and come out on the other end having learned nothing. You will learn something about the line, about the processes, about the variability. You will learn something. So you will be better off, and your line will be better off on the other end. Agree with that?
Now, I remember a plant manager told me one time, this was on a simulation project, it was about a $3 million transformation to take a kind of a departmentally oriented factory and put it into a flow. But it was going to be about a $3 million investment, not insignificant. And this plant manager said, guys, I know it's going to cost some money to build this model. It's going to take, and it's going to delay potentially the project a little bit while that happens. But he said, you know what? I don't care if we learn nothing, because if this doesn't work, if we're not successful with this flow project, I'm going to get fired. So I'm going to take part of that budget and I'm going to invest it in building the simulation model purely as an insurance policy. Well, guess what? It was an insurance policy, but we learned a lot by doing it. So that wasn't the case. But he was willing to even take that step and say, I'm happy if we don't learn anything, just to make sure that what we do works, right?
Well, we recently supported one of our clients in redesigning a line, and between the cost of expanding the building and expanding the line, we helped the client spend more than $2 million. That is a substantial amount of money, and you don't want to go into a project like that without as much data as you can, right? So you need to have as many assurances as you can that your design is a solid design, and for that, simulation model just adds a very good layer of protection.
Okay, next benefit is called Kaizen the Design. So what we have in mind here is, as you build the model and look for opportunities for improvement, you may come up with some new ideas you want to try out. Now, if this were the physical world, you'd have to try it out physically. You'd have to implement your Kaizen suggestion and see if it works or not. Fortunately, in the simulation environment, you can implement your change electronically and test your potential change in that environment first. So it kind of comes back to one of our other benefits of building, not building without testing it first. So you not only are we talking about testing the design, we're talking about testing any change that you might propose to that. Again, before you get to even the detailed CAD design layout stage or the physical implementation stage. So Kaizen the Design.
Without simulation model, all you can do is to err on the side of caution, and on any processes or any process that you foresee a high level of variability, just always round up or add more resources. well, there may be other things you can do, like running a different sequence, right, through that process, and that may prevent you from adding a workstation. You will not know that until either you bring it live and test it, by which time may be too late, or by running a simulation model.
Very good. And the last benefit, we titled this one, helps you to complete the design.
A line design, we said this a couple of times, but it bears repeating. A line design is not just physical resources linked and balanced. That is not a complete design. There are more things. In-process Kanbans, buffers, right? All the procedures to make the line run, like figuring out the sequencing rules, all those aspects of the line, you're not going to calculate those, right? In some cases, some IPK, some buffers you can calculate, but in many cases, you will get a much better resolution from a simulation model than you do by either guessing or by waiting until you bring it live. And that is a complete line design. So what are the things, Richard? Yeah, the sequencing rules. Actually, we had a question this week about sequencing rules, right? Or figuring out sequencing. And that's the topic we're going to address. And this is something we do constantly using simulation modeling. And that allows us to help our clients develop sequencing rules by testing them with simulation.
Yeah, and a good creating a good staffing plan and a good flexing strategy. That's something you need to think through and test in that modeling environment as well, right before you actually do it. Okay, so I think we've covered the 7. Test without building it, test many iterations, forces deep understanding, generates valuable metrics, you learn new things, you Kaizen the design ahead of time, and it helps you to deliver a complete design with all of these details like sequencing rules, buffer sizes, etc. Pretty good deal.
Yeah.
Yeah, so to me, where do I sign up?
Okay. So with that, we're going to bring this one to a close. And we're going to ask you to see us again for one more webinar on this topic, and that we're going to talk about the risks or things to consider when you plan to build a simulation model. Okay, we're back.
You are live. We are live. Well, welcome back to the last of the 4-part series, last webinar. And in this one, we're going to talk about the considerations, say the 4 considerations involved with creating a simulation model. But before we do that, let's recap. Let's kind of summarize our journey so far in this webinar series. Gerard, why don't you review for us, if you don't mind, the skills, the 5 skills that we identified back in the very first one.
Perfect. So on the first webinar of this series, we talked about what are the necessary skills to build a good simulation model. Skill number 1, you need to have a roadmap. You need to have a methodology, because you should never build a model without proper data. And to get that proper data, you have to follow a series of steps. And if you look at the mixed line design roadmap that we teach, you get to build a model after you complete the conceptual line design. Number 1, you need to have a roadmap. Number 2, you needed to get a good and practiced data collection, because the mixed line design roadmap requires quite a bit of data, and you need to understand where to get that data. Is it going to be from your engineering records, from your ERP? Where is it going to be? One of the places where you're going to have to get or validate that data is related to your next skill number 3, and that is interviewing. You need to know how to talk to people to get the best possible data to build your static model and then your simulation model. Also, you needed to have computer skills. And then again, depending on the type of model, simulation model packaging you use, your computer skills are going to go from something simple like what we have with the Lean Design Simulator, which is primarily Excel, or if you have some other modeling tools, you may have to be proficient at coding. So you will need computer skills. You need to decide what level. That's number 4. And finally, communication skills. Once you run the model and you reach conclusions, you need to be able to explain those to your management team, to the line design team, and to the folks that do the work on the line. So those are your 5: the roadmap, data collection, interviewing, computer skills, and communication. Richard, do you think you could do the next section on the prerequisites for building a successful model?
I'll try. So here we go. So once we have those skills in place, or you're confident those skills are available to you on the team, then we have, as a reminder, 3, I'm going to call them, well, the prerequisites or success factors that you need to keep in mind. And the first one is you need to clearly define upfront the goals for the simulation project. And the reason for that is once you've defined your goals, you can make sure that model is able to meet those goals. And it's entirely conceivable that you could have goals and the model is not actually able to answer the questions or achieve those goals because of the way it was designed and structured. So clearly define what is it you want to get out of this simulation model building effort. Second thing is make sure the model works right. Make sure the model is running. It's really disastrous to have a model and the team is not sure that it's working right. So one way to do that, of course, is to set all your times to 1 minute and just make sure all your connections are there. You don't have any orphans, that any percentages you have in there are running as expected. So that's number 2. And then the number 3 is we suggest validating your model, not in terms of just basic functionality, but actually ability to model reality by putting in actual data and running that model against the current state. Because that way you can compare actual performance, assuming you have an existing line, actual performance with the model results, and they should be equivalent. And if they're not, you need to dig into why that model, that computer model, is not reflecting what's actually happening in the value stream. So those are the 3 important success factors that you need to include in your thinking in these projects. Now, we identified 7 benefits. Gerard, you want to review those? The 7 main benefits of wanting to do a simulation project like this?
Absolutely. Benefit number 1, you can test the line without building it, right? Because that happens in the model. Second, you can test many iterations. The computer time or simulation time is a fraction of actual elapsed time. So within 20 seconds, you can model an entire day of production. Third, it will force a deep understanding of your line and your processes. You will have to delve deeper into each process and understand. So third, it forces a deep understanding. Fourth, is going to generate very valuable metrics. You will never be able to see the individual performance of each station and each IPK just from observation. You will get that from a simulation model. Fifth, you will learn new things for sure. It is impossible to think that after going through the roadmap and building a simulation model and running the simulation model, you will learn nothing new on the other end. So you will learn new things. 6, you will be able to Kaizen the design. You will be able to improve your design by running a simulation model. And finally, it will help you complete your line design, because through running the model, you will be able to develop all the necessary procedures and rules and tools to complete the line design. A line is not just a set of linked and balanced resources. is also the how to run the line. So those are your 7 benefits. So should we wrap this up with the 4 considerations, 4 things that the folks thinking about becoming simulationists? That's a new word that you made up, I think. Thinking about
that's a good word. That's a perfectly good word.
Let's talk about those 4. Do you want to get going now?
Yeah. So we might, if we just stop now, we might have left you with the impression that creating a simulation model is just a bed of roses. But there may be some thorns on those roses that we wanted to identify. So considerations, before you jump in with both feet on a project like this. And the first one is that it's going to cost you some money. Now, how much money? Well, it depends on how much you can do yourself. Do you have to hire an outside company to help you? What kind of software are you using? What we're trying to do with our Lean Design Studio and the Lean Design Simulator is to make it easier, and therefore less costly, of course. But there is a cost involved, and so you'll need to include that in your budget. And what we say is that if you have a development budget or a project budget, part of that budget should be dedicated to this. But how much do you need to budget? Well, that's again going to depend on the complexity of the project. Is it a huge effort? Is it a small line? So there's a wide range of possible costs, but it will cost you some money to do that.
Yes, and in most of
and what else is money, Gerard? Question for you.
Exactly right, which is the second consideration: time. It will cost you time, and the time will be in the form of learning how to build a model, building the model, testing the model, getting the results, and presenting them. So time is a very important factor. You have to keep that in mind. Now, you could also say, well, this is going to delay the line setup. Don't look at it as delaying, right? Yeah, you may have to postpone it for a few days, but it will be a much better line, and you will go into it. You will bring that line live with a much higher degree of confidence. So number one, it will cost you a few bucks, depending on what you're planning to use. We're trying to do something about that by making it easy for our students. And secondly, it will cost you time. So
and the time, the time budget, hopefully most of that time budget can be dedicated to running experiments, trying different scenarios, and improving the design, as opposed to time spent trying to build the model and get it working. So I think we're making a major contribution in that regard with the Lean Design Simulator in terms of making it easier to actually build the model itself and get you to that point where you can run experiments and try things out much more quickly.
We have clients that are very keen on using simulations because their lines are very expensive to build. And I mean very expensive, where a workstation costs hundreds of thousands of dollars and take a lot of space. So they want to use simulation, but the simulation packages they have sometimes are so complex that they end up with one department, and then that one department doesn't have enough volume, so they end up with one individual department at the corporate level. So then what happens is that the plant in Spain goes through a line design, and then they have to submit the data to the modeling department that happens to be in Australia, and then wait for the answer. That will cause some consternation on the folks designing the line. And then again, that is one thing we're trying to solve with the Lean Design Simulator. We're not going to sit here and tell you, and our Lean Design Simulator will compete with some of the simulation modeling tools that cost tens of thousands of dollars. That's not us. Trust me. If you need to simulate the functioning of an airport, go with them guys. But for a line, for a value stream, I think we have it covered.
Okay, very good. So time and money, we covered those two.
Yeah.
Now what else? The third consideration, and Gerard mentioned earlier to me, well, this is kind of obvious, but we'll say it again, it's getting or having management support for these efforts. You can imagine getting someone, you could imagine maybe yourself being very excited about simulation and going off and building a model and actually learning a lot and coming up with some improvement ideas. But if you haven't had that buy-in up front, then you're going to have trouble taking it beyond just your own learning experience. Because until you lay the groundwork and get actual approval and engagement from management and your colleagues, you're going to be working on your own, I'm afraid. So getting management support, developing that ahead of time, and building that is really critical.
And this also becomes a question of experience, right? Because I remember one of my projects not long ago, we used the simulation model as an excuse to invite our executive sponsor along with the line design team and say, hey, could you please join us? We're going to be running simulations on the line design we're going to propose. We want you to see it. So they are present. They're always present when I run those, and it always generates. It always has a wow effect, right? See, this is the line that we're going to build for you. Are you satisfied? And we always get the nod. Keep them appraised. Provide them with data.
Okay. And then the very last one, you mentioned the magic word data.
Yeah,
the last one on our list of considerations is have good data. Again, obvious, right? Have good data. And on the roadmap, there's a phase, data collection, which happened before this simulation project. But the reason we're mentioning this again is even though you may have done your due diligence at the data collection phase, and we hope you did, and we hope that all that data is good, when you get to the simulation stage, you might find that some, shall we call it data collection rework, might be necessary. Because if your model does not match the current state, you're going to have to dig into why, and there are various reasons why it may not match, but one of them might be the data that you've collected. So that would be a good thing to learn, but it points to an issue outside of simulation potentially, right, in terms of cleaning up data. So in other words, do not assume that the data you've collected earlier, even though you expect it's good data, don't assume that it is, because you're going to be testing it against reality within the simulation model. So if you don't have good data, you're pretty much at a stopping point in terms of being able to go forward, right? You're going to have to.
Things to consider when you're building a simulation model. It's going to cost you $1. It's going to take some time. You need to make sure that you have management on your side, and you need to make sure you have good data. This is the opportunity to ensure that you have good data. The simulation model will be the acid test for the data you gather to build the static line design mathematics. Beautiful.
Love it. One last story that I think you'll find interesting. When we look at, back to our original question, is lean compatible with computer modeling or simulation modeling? Question mark. When we go back to that original question, sometimes we ask ourselves, and Gerard, you and I have talked about this many times, who do we look to in the world as the gold standard for lean? And most of us would, I think, tend to agree that the gold standard for lean practices and lean culture is Toyota. Would you agree with that? You can mention their name.
Nobody in his right mind would argue that.
Right.
Of course it is Toyota.
So here's the story. About a month ago or so, I was on the phone with a representative from ProModel Corporation. Now, ProModel is one of the big simulation modeling software companies. One of the major ones. And I was chatting with him about maybe doing some partnership or working together. And he said to me two very interesting things I'll share with you. First thing he said was, you know, the methodology you guys teach is pretty much very well aligned with the needs of building a simulation model. This roadmap we've talked to you about. He said the roadmap, which he was familiar with, this roadmap is very closely aligned with the kind of effort you'd have to go through anyway if you're building a simulation model, because the data you guys collect and the way you analyze it and the way you put it together is really what a simulation model needs. So that was great to hear that, right? That was great confirmation that this roadmap we've been mentioning is really the right tool, the right approach, and simulation is a part of that. But here's the other interesting thing he said. He said, you know, there are companies that are embracing, a lot of companies are embracing simulation modeling in a big way. And he said, and just between you and me, one of them is Toyota, embracing simulation modeling within Toyota itself, specifically Toyota Motor Company. So I thought, well, that was a piece of new information because I didn't really know, but he confirmed, because he's on the inside, that Toyota itself, the great Toyota itself, is actually using simulation modeling not in a little way, in a big way, he said. So it provides some external validation for this whole issue we've been talking about in this webinar, that this is a good thing to embrace and learn and use. Okay, so with that, I think we reached the end of this webinar series.
Yep. So
thanks for sticking with it.
Thank you for sticking with it. Please watch all 4. We made them short enough so you can watch them many times. Thank you all for participating as always, and we'll stay in touch. Until next time.
Yeah, I know.